Okay, let's just goon a little bit. Let's max out our divine intellect. Is this negalicious or is this divine intellect? Okay, let's work on something. Let's look at this. I wanna why am I so sick? No, no, Bernoulli distribution and binomial distribution classification. Dun, 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 dun. So this is okay, bro. We're doing too much. So what is Bernoulli distribution? Yeah, I literally don't need this. I could just so Bernoulli distribution. Okay, I need to write something down. I need to write everything down because I said so. Because some blah blah blah. Because some because I'm happy now. Maybe I should show my beautiful face. Show my beautiful face. Oh, it's over there. Show my beautiful face. Show my beautiful face. It's always flipped. Always flipped. Always spiking my cortisol. I used to be a I used to be cortisol spiker because David Goggins and all of them people. But nowadays I'm like, not worth it. Spiking your cortisol, definitely not worth it. Taking risk, you need to do it because I think it kind of helps. When you take a lot of risk, it genuinely kind of helps. Spiking your cortisol, definitely not a good move. But taking risk while spiking cortisol, bro, best case scenario. You know what I mean? Like, why do you wanna work so hard? Like you could just jester goon all day. Jester gooning, it's like one, you're just keeping the morale of the team a little bit higher. So okay. Let's bro, lot of moving things. Fucking bitch. Gucci flip flops. Bernoulli distribution models. a single trial or experiment that has only two possible outcomes, typically labeled as success with a probability p or failure with probability 1 minus p. Okay. Not sure how we got here, but fucking dope. Fucking dope, mate. Let's fucking go. You know what I mean? Distribution. So we have a lot of types of distribution. Hmm. No, I don't need the map. Okay. Normal Gaussian theorem. Key probability distribution. Joint marginal condition. Okay, let's see what joint marginal condition is. Because inference comes from machine learning. Okay. Bernoulli binomial. It's I don't know what is binomial. I kind of like started on it, but I haven't done. Oh no, Bernoulli. Let's check this out. So, uh, Bernoulli. Why is this like this? So it's either true or okay. It's either false. Okay, P. What is P? P is the probability of value. Okay, P of minus one. So let's say P is one. So one is true. Okay, P is true. If P is zero, you have two peaks. Why is that? Okay, P is the probability of it happening of P of 1 of minus P of 1. It's the P is the mean and P minus, okay, makes sense, I guess. So this goes to 1. How about both like kind of goes down to the same output though. I mean, it doesn't matter. Oh, it always goes to 1 because the bottom slider, the orange slider, will be the function culminative distribution. And yeah, that makes sense. That makes total sense. That makes total sense. That makes total sense. Binomial geometric. Hmm. What is going on with geometric, bro? Other central limit theorem is same as normal distribution. I guess not. I guess not. This is Poisson. like a negative binomial. Oh, it has bro. We're just describing the same. You're just like describing a graph, like different names and like different functions. Okay, so this will be the PMF. Okay, that makes sense, kind of. So this is discrete, something you're counting, and this is something measured. Let's go here. Uniform, same. Oh, you just like measured. It's just like get measured. You're not really like counting it. This is just a function acting on it. So normal, of course. This is essentially half of the graph. This is 100%, nearly 100% of the graph. So I think that's what it means here. 60% of the graph, 100% of the graph. Okay, that's one way to look at it. So this is the normal distribution formula. We need to like see how it's represented in other things. Student T. Okay, same thing. No? Yeah, okay. Student T is similar to a normal distribution. Chi-square. Chi-square, it's, ooh, what's going on here? Slim Shady. Hi, my name is Hi. My name is Hi. My name is Slim Shady. Hi, my name is Hi. Okay. Um. Whoa, it's like a wave. Look at it. So this is chi-squared for some reason, and let's look at it. Huh. Okay. That kind of makes sense. Kind of makes sense. Because it kind of makes sense. Because niggas is in Paris. Because niggas is in Paris, bro. You're a jester. I'm like, whoa, whoa. Is this niggerlicious or is this divine intellect? This is half of the graph essentially, half of the population density. Culmination, half of the culmination, you can call it. So this is the half, this is the gamma distribution. It looks something like this. Don't know why it has that kind of shape. It kind of like appears in nature when we're trying to like give a name for it. Beta. This is beta. So yeah, it kind of makes sense. Okay, this will be half of the population. So what is beta? Oh, we could like play with this. Okay. Yeah, some angles alpha beta going on. Bro, I remember doing this probability. I think the top one collapses. Looks like a football club Malta shirt. If you know, you know. Ooh, look at that. It's like a nip slip. A bitch is trying to do a nip slip. Oh, take a look at my tits. That's her saggy little tits. This is, when you like see women with like uneven like breast size, one tits is like so much bigger than the other one. That's this. That's the beta distribution. Fucking beta mill. So okay, so it's all continuous. This is discrete, something you're counting, right? I can do that. I didn't know that. Beta. So these are the types of distribution that could happen, and these are the culmination of things. Which is a little bit- So it depends. What kind of distribution are we using? Dun, 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 dun. Dun, 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 dun. You see a small set of distribution. It's like a normal distribution. Normal slash Gaussian binomial slash Bernoulli binomial. Bernoulli. Discrete when, okay, probability is continuous, using models of real value or noise, feature residues, and continuous variables. Okay. Most common practice, normal. Assume noise in linear algebraic or logarithmic logistic regression. Logarithmic, logistic. Okay. What is the difference between logistic and logarithmic? Who knows? I need an A4 sheet. Okay. Um, Bernoulli. So categorical multinomial and Poisson for Bayesian and general stuff. Beta, fucking beta. Beta is that. It has that shuk 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 and reshit. So we have normal Bernoulli. So what is this one doing? Could you go down, Mister? Oh, that's already down. ROC curve. What is this? Precise recall of curvature comparison. Confusion matrix. That's pretty cool. Its confusion matrix is pretty that kind of like Bayesian statistics type shit, right? Save the best model hybrid. What the hell? A data set is highly imbalanced. 5% fraud. High. Okay. AOC 95% achieved. I think AOC is just like a test. ROC and AUC. Most features amount, transaction velocity, hour. Deploy model via fast API containerized. Deploy Kubernetes monitor with Prometheus. Okay, that's a lot of tech. A lot of tech involved. So what are they using? What are they using? So they should probably feature importance hybrid model. No way. Uh, they don't understand the things I say on Twitter. All my brother's Christian's brother. Hallelujah. Precise recall curvature comparison. Okay. How do I see? Okay, okay, okay. Evaluate all models. That's model evaluation. I haven't even done the trained models or different resampling strategies. Random forest classifier, and we have X scale, Y scale train, random forest classifier. Okay. What is the distribution of it? What is the distribution? I mean, distribution is just like a superficial word that we give. Hybrid, somewhat and undersampling, oversampling, baseline. Okay. Yo, pam bam 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 bam. So this is the confusion matrix, I guess. Feature correlation heat map. So Mount Howard. Okay, that's like this diagonal matrix. It's gonna nifty. Kinda nifty. It's kinda nifty, Donald Trump. It's kinda nifty, you know. Transaction amount. Okay. So what is going on? Transaction velocity, merchant category, uh, our distribution, forward, our normal. Okay, it's a normal distribution. Okay, it's happening a normal distribution. So this is the okay. I Linus is gonna beat your ass, bro. He's gonna beat your ass, Bucko. I need to be in a Python environment. That's go into the Python environment, please. Was not created because it's not available. Install. Install. Okay. Unable to acquire. Yeah, buddy. Sure. Unknown. Scout is an unknown command. So let's just be a really good engineer. Let's be a real nigger, please. Can the real nigger stand up? I need to take a piss. I'm gonna bring an A4 sheet with me. I'm a black star, I'm a star star. Fucking nigga. Nigga, please. Did I catch you on some B shit? Okay. Okay, let's, while that is going on. So... normal distribution, Bernoulli slash binomial distribution, categorical slash multinomial distribution, Poisson, uniform, beta, Dirichlet. When you go deep pork, first really initialize Gaussian and Bernoulli distribution categorical multimodal. Control T. I'm a rock star, I'm a star. Fatal. The fuck? Bro, I don't know what's going on. Just copying and pasting code.
So let's look at Poison. So Poison, binomial Bernoulli, beta, that's continuous, uniform, normal, of course, beta, categorical multi, fuck. What the fuck is Nginx? I don't know what Nginx does. If corrupted. What does it do? So I haven't written a package yet. So there's a lot of images in my Docker, I guess. So I'm cleaning the okay. Someone have to program all that. So what is Trivi image? What is going on? Wait. Okay. I thought something else went off. Clean all. What is Trivi? Java vulnerabilities. Are we using Trivi? Oh yeah, I need to put in an info sheet. Fucking work? Why don't you work? Images. Oh, fuck. Docker images.
Mm. Bro, of course. Of course, brother.
job lib. Okay. Equation.
Welcome back. So we're talking about probability distributions and random variables x. And today I'm going to introduce two of the most useful random variables, the Bernoulli distributed random variable and the binomial distributed random variable. And from binomial, we're going to get the normal distribution, Poisson processes, lots of really useful models of real-world phenomena come out of these two basic random variables. So let's get started. We've talked a lot about we've talked kind of fast and loose about a lot of probabilities. We've computed the probability of coin flips. We've computed the probability of getting 5 heads in a row or getting at least 5 heads out of 10 coin flips. We've talked about dice rolls and poker hands and all kinds of stuff. But we've made some kind of assumptions that right now we're going to formalize. So for example, I've been assuming that my coin has an equal probability of flipping heads or tails. So I've been assuming that each of these has 1 in 2 or 50% probability. I'm going to start with the Bernoulli random variable. So a Bernoulli random variable x, a Bernoulli random variable x can only take 2 values, 0 or 1. Can take 2 values. So we say that the range is either 0 or 1. It can either be 0 or 1. And I could say heads is 1, tails is 0, or vice versa. It's just about how you define it. I could also define my dice roll as a random variable if my random variable is, did I get a 6 on that dice roll? If my random variable is whether or not I got a 6 on that dice roll, the range would be a 0 or a 1. 0 means I did not get it. 1 means I did get it. Okay, so the range is either 0 to 1. This
Let's say that I'm able to go out and survey every probability distribution. It's going to be a discrete one because there's only two values that any person can take on. They could either have an unfavorable view, or they could have a favorable view. Or they could have a favorable view, and 40% have an unfavorable view. 40% have an unfavorable view, and let me color code this a little bit. So this is the 40% right over here, so 0.4. Maybe I'll just write 40% right over there, 40% right over there, and then 60%, have a favorable view. Have a favorable view, 60%. Let me color code this. 60% have a favorable view. And notice these two numbers add up to 100% because everyone had to pick between these two options. Now, if I were to go and ask you to pick a random member of that population and say, what is the expected favorability rating of that member? What would it be? Or another way to think about it is, what is the mean of this distribution? And for a discrete distribution like this, your mean or your expected value is just going to be the probability weighted sum of the different values that your distribution can take on. Now, the way I've written it right here, you can't take a probability weighted sum of u and f. You can't say 40% times u plus 60% times f. You won't get any type of a number. So what we're going to do is define u and f to be some type of value. So let's say that u is 0, and f is 1. And now the notion of taking a probability weighted sum makes some sense. So the mean, or you could even say the mean, well, I'll say the mean of this distribution is going to be 0.4. It's going to be 0.4. That's this probability right here, times 0, plus 0.6 plus 0.6 times 1, plus 0.6 times 1, which is going to be equal to, this is just going to be 0.6 times 1 is 0.6. So clearly no individual can take on the value of 0.6. No one can tell you I 60% am favorable and 40% am unfavorable. Everyone has to pick either favorable or unfavorable. So you'll never actually find someone who has a 0.6 favorability value. It'll either be a 1 or 0. So this is an interesting case where the mean or the expected value is not a value that the distribution can actually take on. It's a value someplace. It's a value someplace over here that obviously cannot happen. But this is the mean. This is the expected value. And the reason why that makes sense is if you surveyed 100 people, you multiply 100 times this number, you would expect 60 people to say yes. Or if you sum them all up, 60 would say yes, and then 40 would say 0. You sum them all up, you would get 60% saying yes. That's exactly what our population distribution was. Now what is the variance? What is the variance of this population right over here? So the variance, let me write it over here. Let me pick a new color. The variance is just, you could view it as the probability weighted sum of the squared distances from the mean, or the expected value of the squared distances from the mean. So what's that going to be? Well, there's two different values that anything can take on. You can either have a 0 or you could either have a 1. The probability that you get a 0 is 0.4. So there's a 0.4 probability that you get a 0. And if you get a 0, what's the distance from 0 to the mean? The distance from 0 to the mean is 0 minus 0.6, or I can even say 0.6 minus 0, same thing because we're going to square it. 0 minus 0.6 squared. Remember, the variance is the probability or the weighted sum of the square distances. So this is the difference between 0 and the mean. And then plus, there's a 0.6 chance. There's a 0.6 chance. 0.6 chance that you get a 1. The difference between 1 and 0.6. 1 and our mean, 0.6, is that. And then we are also going to square this over here. Now, what is this value going to be? This is going to be 0.4 times 0.6 squared. This is 0.4 times the 0 minus 0.6 is negative 0.6. If you square it, you get positive 0.36. So this value right here, I'm going to color code it. This value right here is times 0.36, and then this value right here, let me do this in another, so then we're going to have plus 0.6 plus this 0.6 times 1 minus 0.6 squared. Now 1 minus 0.6 is 0.4. 0.4 squared, or 0.4 squared, is 0.16. So let me do this. So this value right here is going to be 0.16. Let me get my calculator out. Is equal to 0.24. 0.24. So our standard deviation of this distribution, is 0.24. Or if you want to think about the variance of this distribution is 0.24, and the standard deviation of this distribution, which is just the square root of this, the standard deviation of this distribution is going to be the square root of 0.24. And let's calculate what that is. That is going to be, let's take the square root of 0.24, which is equal to 0.48. Well, I'll just round it up, 0.49. So this is equal to 0.49. So if you were to look at this distribution, the mean of this distribution is 0.6. So 0.6 is the mean, and the standard deviation is 0.5. So the standard deviation is, so it's actually out here, is, because if you go add one standard deviation, you're almost getting to 1.1. So this is one standard deviation above, and then one standard deviation below gets you right about here. And that kind of makes sense. It's hard to really kind of have a good intuition for a discrete distribution, because you really can't take on those values, but it makes sense that the distribution is skewed to the right over here. Anyway, I did this example with particular numbers, because I want to show you why this distribution is useful. In the next video, I'll do these with just general numbers, where this is going to be p, where this is the probability of success, and this is 1 minus p, which is the probability of failure. And then we'll come up with general formulas for the mean and variance and standard deviation of this distribution, which is actually called the Bernoulli distribution. It's the simplest case of the binomial distribution.
Let's derive the mean and variance of the Bernoulli distribution. Here's the probability mass function for the Bernoulli distribution. And sometimes I take a bit of a shortcut and write this as p of little x. And the Bernoulli random variable can take on the values 0 or 1. And in this video, I'm going to show that the mean, or expectation, of a Bernoulli random variable x is equal to p, and sigma squared, or the variance of a Bernoulli random variable x, is equal to p times 1 minus p. Here again is the probability mass function for the Bernoulli distribution. And the expectation of a discrete random variable x is equal to the sum over all
Welcome back. Okay, so in the last couple of lectures, we have defined the expected value of a distribution x, this kind of expectation of a random variable x, which measures the center of mass of that distribution. For nice, well-behaved distributions like a Gaussian, it is actually the most probable and center of the distribution. Today, we're going to introduce the variance and standard deviation of a random variable x. So if the mean, mu, is the measure of center of mass of the distribution, then the variance of x, and I'll define it in a minute, the variance in x measures the average squared deviation of x from that mean value. This measures the average square deviation of x from this mean value mu. And the standard deviation is just the square root of the variance. So let me draw a really quick picture here because I think this will help. Maybe I'll start in yellow. So let's say I have some probability distribution function like this nice Gaussian. Then the mean, the expected value, is the kind of center of this distribution, mu. The variance is how much spread, what is the expected squared deviation of x from this mean value, mu. And maybe I'll also write down the standard deviation. The standard deviation of x, SD of x, this is essentially measures the spread. And spread is a non-technical word. We can kind of define it as the standard deviation if you want. The spread of the histogram of the PDF of x. So for example, in the Gaussian normal distribution, the standard deviation are these plus or minus kind of sigma points, plus or minus sigma, where sigma is the standard deviation, inside of which about 68% of the distribution lives within plus or minus one sigma, and then you have two sigma, two standard deviations, 3, 4, 5. So mu measures the center of mass, standard deviation measures the spread, and the standard deviation, SD of x, is just the square root of the variance of x. Okay, so I'm going to write down now what the formula is for the variance. We're going to show kind of how it works and how to compute it, and then zoom back out and talk about it with respect to these distributions. Okay, and this is a really, really easy idea here. So let's start with this variance of x, and maybe I'll just do it over here for a minute. So the variance of x is defined. This is kind of the definition, so maybe I'll do like a little triangle equals. This is defined as the expected square deviation of x from mu. It's a weird mouthful. I'll write it down in math. It's actually going to be more sensible in math. It's the expectation of my variable x minus the mean quantity squared. So we know that mu is the mean value, it's the average value, but if my distribution has some spread, if I randomly sample values of x, they're probably not going to be exactly equal to mu. There's going to be some x minus mu. So what is the expected value of the square of that spread, the square of the difference between x and mu? What's
Hello again. In this lecture, we are going to discuss the Bernoulli distribution. Before we begin, we use Bern to define a Bernoulli distribution, followed by the probability of our preferred outcome in parentheses. Therefore, we read the following statement as variable x follows a Bernoulli distribution with a probability of success equal to p. Okay, we need to describe what types of events follow a Bernoulli distribution. Any event where we only have one trial and two possible outcomes follows such a distribution. These may include a coin flip, a single true or false quiz question, or deciding whether to vote for the Democratic or Republican parties in the US elections. Usually when dealing with Bernoulli distribution, we either have the probabilities of one of the events occurring or have past data indicating some experimental probability. In either case, the graph of a Bernoulli distribution is simple. It consists of two bars, one for each of the possible outcomes. One bar would rise up to its associated probability of p, and the other one would only reach 1 minus p. For Bernoulli distributions, we often have to assign which outcome is 0 and which outcome is 1. After doing so, we can calculate the expected value. Bear in mind that depending on how we assign the 0 and the 1, our expected value will be equal to either p or 1 minus p. We usually denote the higher probability with p and the lower one with 1 minus p. Furthermore, conventionally, we also assign a value of 1 to the event with the probability equal to p. That way, the expected value expresses the likelihood of the favored event. Since we only have one trial and a favored event, we expect that outcome to occur. By plugging in p and 1 minus p into the variance formula, we find that the variance of Bernoulli events would always equal p times 1 minus p. That is true regardless of what the expected value is. Here's the first instance where we observe how elegant the characteristics of some distributions are. Once again, we can calculate the variance and standard deviation using the formulas we defined earlier, but they bring us little value. For example, consider flipping an unfair coin. This coin is called unfair because its weight is spread disproportionately, and it gets tails 60% of the time. We assign the outcome of tails to be 1 and p to equal 0.6. Therefore, the expected value would be p, or 0.6. If we plug in this result into the variance formula, we would get a variance of 0.6 times 0.4, or 0.24. Good job, everybody.
If you found this video interesting and want to gain an edge in your career, make sure to like, comment, and subscribe. And don't forget to check out some of our other
StatQuest is cool, that's my opinion. If you don't think so, then your opinion is inversely correlated with mine. StatQuest. Hello.
You're buying a product online, and you see 3 different sellers. They're all offering that same product at essentially the same price. One of them has a 100% positive rating, but with only 10 reviews. Another has a 96 positive rating with 50 total reviews, and yet another has a 93% positive rating, but with 200 total reviews. Which one should you buy from? I think we all have this instinct that the more data we see, it gives us more confidence in a given rating. We're a little suspicious of seeing 100% ratings, since more often than not, they come from a tiny number of reviews, which makes it feel more plausible that things could have gone another way and given a lower rating. But how do you make that intuition quantitative? What's the rational way to reason about the trade-off here between the confidence gained from more data versus the lower absolute percentage? This particular example is a slight modification from one that John Cook gave in his excellent blog post, A Bayesian Review of Amazon Resellers. For you and me, it's a wonderful excuse to dig into a few core topics in probability and statistics. And to really cover these topics properly, it takes time. So what I'm going to do is break this down into 3 videos, where in this first one, we'll set up a model for the situation and start by talking about the binomial distribution. The second is going to bring in ideas of Bayesian updating and how to work with probabilities over continuous values. And in the third, we'll look at something known as a beta distribution and pull up a little Python to analyze the data we have and come to various different answers depending on what it is you want to optimize. Now, to throw you a bone before we dive into all the math, let me just show you what one of the answers turns out to be, since it's delightfully simple. When you see an online rating, something like this 10 out of 10, you pretend that there were 2 more reviews, one that was positive and one that's negative. In this case, that means you pretend that it's 11 out of 12, which would give 91.7%. This number is your probability of having a good experience with that seller. So in the case of 50 reviews, where you have 48 positive and 2 negative, you pretend that it's really 49 positive and 3 negative, which would give you 49 out of 52, or 94.2%. That's your probability of having a good experience with the second seller. Playing the same game with our third seller who had 200 reviews, you get 187 out of 202, or 92.6%. So according to this rule, it would mean your best bet is to go with seller number 2. This is something known as Laplace's rule of succession. It dates back to the 18th century. And to understand what assumptions are underlying this, and how changing either those assumptions or your underlying goal can change the choice you make, we really do need to go through all the math. So without further ado, let's dive in. Step 1, how exactly are we modeling the situation, and what exactly is it that you want to optimize? One option is to think of each seller as producing random experiences that are either positive or negative, and that each seller has some kind of constant underlying probability of giving a good experience, what we're going to call the success rate, or S for short. The whole challenge is that we don't know S. When you see that first rating of 100% with 10 reviews, that doesn't mean the underlying success rate is 100%. It could very well be something like 95%. And just to illustrate, let me run a little simulation, where I choose a random number between 0 and 1, and if it's less than 0.95, I'll record it as a positive review, otherwise, record it as a negative review. Now do this 10 times in a row, and then make 10 more, and 10 more, and 10 more, and so on, to get a sense of what sequences of 10 reviews for a seller with this success rate, 0.95, would tend to look like. Quite a few of those, around 60% actually, give 10 out of 10. So the data we see seems perfectly plausible if the seller's true success rate was 95%. Or maybe it's really 90% or 99%. The whole challenge is that we just don't know. As to the goal, let's say you simply want to maximize your probability of having a positive experience, despite not being sure of this success rate. So think about this here. We've got many different possible success rates for each seller, any number from 0 up to 1. And we need to say something about how likely each one of these success rates is, a kind of probability of probabilities. Unlike the more gamified examples like coin flips and die tosses and the sort of things you see in an intro probability class, where you go in assuming a long-run frequency, like 1/2 or 1/6, what we have here is uncertainty about the long-run frequency itself, which is a much more potent kind of doubt. I should also emphasize that this kind of setup is relevant to many, many situations in the real world where you need to make a judgment about a random process from limited data. For example, let's say that you're setting up a factory producing cars, and in an initial test of 100 cars, 2 of them come out with some kind of problem. If you plan to spin things up to produce 1,000,000 cars, what are you willing to confidently say about how many total cars will have problems that need addressing? It's not like the test guarantees that the true error rate is 2%, but what exactly does it say? As your first challenge, let me ask you this. If you did magically know the true success rate for a given seller, say it was 95%, how would you compute the probability of seeing, say, 10 positive reviews and 0 negative reviews, or 48 and 2, or 186 and 14? In other words, what's the probability of seeing the data given an assumed success rate? A moment ago, I showed you something like this with a simulation, generating 10 random reviews. And with a little programming, you could just do that many times, building up a histogram to get some sense of what this distribution looks like. Likewise, you could simulate sets of 50 reviews and get some sense for how probable it would be to see 48 positive and 2 negative. You see, this is the nice thing about probability. A little programming can almost always let you cheat a little and see what the answer is ahead of time by simulating it. For example, after a few 100,000 samples of 50 reviews, assuming the success rate is 95%, it looks like about 26.1% of them would give us this 48 out of 50 review. Luckily, in this case, an exact formula is not bad at all. The probability of seeing exactly 48 out of 50 looks like this. This first term is pronounced 50 choose 48, and it represents the total number of ways that you could take 50 slots and fill out 48 of them. For example, maybe you start with 48 good reviews and end with 2 bad reviews, or maybe you start with 47 good reviews and then it goes bad, good, bad, and so on. In principle, if you were to enumerate every single possible way of filling 48 out of 50 slots like this, the total number of these patterns is 50 choose 48, which in this case works out to be 1,225. What do we multiply by this count? Well, it's the probability of any one of these patterns, which is the probability of a single positive review raised to the 48th times the probability of a single negative review squared. Crucial is that we assume each review is independent of the last, so we can multiply all the probabilities together like this. And with the numbers we have, when you evaluate it, it works out to be 0.261, which matches what we just saw empirically with the simulation. You could also replace this 48 with some other value and compute the probability of seeing any other number of positive reviews, again, assuming a given success rate. What you're looking at right now, by the way, is known in the business as a binomial distribution, one of the most fundamental distributions in probability. It comes up whenever you have something like a coin flip, a random event that can go one of 2 ways, and you repeat it some number of times. And what you want to know is the probability of getting various different totals. For our purposes, this formula gives us the probability of seeing the data given an assumed success rate, which ultimately we want to somehow use to make judgments about the opposite, the probability of a success rate given the fixed data that we see. These are related, but definitely distinct. To get more in that direction, let's play around with this value of s and see what happens as we change it to different numbers between 0 and 1. The binomial distribution that it produces kind of looks like this pile that's centered around whatever s times 50 is. The value we care about, the probability of seeing 48 out of 50 reviews, is represented by this highlighted 48th bar. So let's draw a second plot on the bottom, representing how that value depends on s. When s is equal to 0.96, that value is as high as it's ever going to get. And this should kind of make sense, because when you look at that review of 96%, it should be most likely if the true underlying success rate was 96%. As s increases, it kind of peters out, going to 0 as s approaches 1, since someone with a perfect success rate would never have those two negative reviews. Also, as you move to the left, it approaches 0 pretty quickly. By the time you get to s equals 0.8, getting 48 out of 50 reviews by chance is exceedingly rare. It would happen 1 in 1,000 times. This plot we have on the bottom is a great start to getting a more quantitative description for which values of s feel more or less plausible. Written down as a formula, what I want you to remember is that as a function of the success rate, s, the curve looks like some constant times s to the number of positive reviews times 1 minus s to the number of negative reviews. In principle, if we had more data, like 480 positive reviews and 20 negative reviews, the resulting plot would still be centered around 0.96, but it would be smaller and more concentrated. A good exercise right now would be to see if you could explain why that's the case. There is a lingering question, though, of what to actually do with these curves. I mean, our goal is to compute the probability that you have a good experience with this seller, so what do? Naively, you might think that probability is 96%, since that's where the peak of the graph is, which in a sense is the most likely success rate. But think of the example with 10 out of 10 positives. In that case, the whole binomial formula simplifies to be s to the power 10. The probability of seeing 10 consecutive good reviews is the probability of seeing one of them raised to the 10th. The closer the true success rate is to 1, the higher the probability of seeing a 10 out of 10. Our plot on the bottom only ever increases as s approaches 1. But even if s equals 1 is the value that maximizes this probability, surely you would feel comfortable saying that you personally have a 100% probability of a good experience with the seller. Maybe you think that instead we should look for some kind of center of mass of this graph, and that would absolutely be on the right track. First, though, we need to explain how to take this expression for the probability of the data we're seeing given a value of s, and get the probability for a value of s, the thing we actually don't know, given the data, the thing we actually know. And that requires us to talk about Bayes' rule, and also probability density functions. For those, I'll see you in part 2.
StatQuest is cool. That's my opinion. If you don't think so.
Imagine you have a weighted coin, so the probability of flipping heads, it might not be 50-50 exactly. It could be 20%, or maybe 90%, or 0%, or 31.41592%. The point is that you just don't know. But imagine that you flip this coin 10 different times, and 7 of those times it comes up heads. Do you think that the underlying weight of this coin is such that each flip has a 70% chance of coming up heads? If I were to ask you, hey, what's the probability that the true probability of flipping heads is 0.7, what would you say? This is a pretty weird question, and for two reasons. First of all, it's asking about a probability of a probability, as in the value we don't know is itself some kind of long-run frequency for a random event, which frankly is hard to think about. But the more pressing weirdness comes from asking about probabilities in the setting of continuous values. Let's give this unknown probability of flipping heads some kind of name, like h. Keep in mind that h could be any real number from 0 up to 1, ranging from a coin that always flips tails up to one that always flips heads, and everything in between. So if I ask, hey, what's the probability that h is precisely 0.7, as opposed to, say, 0.700000001, or any other nearby value, well, there's going to be a strong possibility for paradox if we're not careful. It feels like no matter how small the answer to this question, it just wouldn't be small enough. If every specific value within some range, all uncountably infinitely many of them, has a non-zero probability, well, even if that probability was minuscule, adding them all up to get the total probability of any one of these values will blow up to infinity. On the other hand, though, if all of these probabilities are 0, aside from the fact that now gives you no useful information about the coin, the total sum of those probabilities would be 0, when it should be 1. After all, this weight of the coin h is something, so the probability of it being any one of these values should add up to 1. So if these values can't all be non-zero, and they can't all be 0, what do you do? Where we're going with this, by the way, is that I'd like to talk about the very practical question of using data to create meaningful answers to these sorts of probabilities of probabilities questions. But for this video, let's take a moment to appreciate how to work with probabilities over continuous values and resolve this apparent paradox. The key is not to focus on individual values, but ranges of values. For example, we might make these buckets to represent the probability that h is between, say, 0.8 and 0.85. Also, and this is more important than it might seem, rather than thinking of the height of each of these bars as representing the probability, think of the area of each one as representing that probability. Where exactly those areas come from is something that we'll answer later. For right now, just know that in principle, there's some answer to the probability of h sitting inside one of these ranges. Our task right now is to take the answers to these very coarse-grained questions and to get a more exact understanding of the distribution at the level of each individual input. The natural thing to do would be consider finer and finer buckets. And when you do, the smaller probability of falling into any one of them is accounted for in the thinner width of each of these bars, while the heights are going to stay roughly the same. That's important because it means that as you take this process to the limit, you approach some kind of smooth curve. So even though all of the individual probabilities of falling into any one particular bucket will approach 0, the overall shape of the distribution is preserved and even refined in this limit. If, on the other hand, we had let the heights of the bars represent probabilities, everything would have gone to 0. So in the limit, we would have just had a flat line giving no information about the overall shape of the distribution. So wonderful, letting area represent probability helps solve this problem. Well, let me ask you, if the y-axis no longer represents probability, what exactly are the units here? Since probability sits in the area of these bars, or width times height, the height represents a kind of probability per unit in the x direction, what's known in the business as a probability density. The other thing to keep in mind is that the total area of all these bars has
In this video, we'll be learning about the binomial distribution. Before we talk about the binomial distribution, let's review the binomial formula. From the previous video, we know that the binomial formula looks like this, where k is the number of successes, n is the number of trials, and little p is the probability of success. If we were flipping a coin 2 times, and if a success is getting heads, we can use this formula to calculate the probabilities for each number of successes. This means that k will be equal to 0, 1, or 2. In this case, k cannot exceed 2, so we are only flipping a coin twice. It would be impossible to see 3 successes, in other words, 3 heads, by only flipping a coin twice. N is equal to 2 if there are 2 trials, and notice because we are flipping the coin for a total of 2 times. Little p is equal to 0.5 because there's a 50% chance of getting heads when we flip the coin. In other words, there's a 50% chance of getting a success. Now that we have identified each variable, we will use the formula to determine the probability of each value of k. After plugging in the necessary values into the formula, you should get 0.25, 0.50, and 0.25. again as your final answers. These are the probabilities for each respective value of k. To visualize the binomial distribution, we will create a bar chart with this data. The number of successes is listed on the x-axis, which is why we have 0, 1, and 2. These are the values of k, and the probability of success for each value of k is listed on the y-axis. So from this bar chart, we can clearly see that the probability of getting 0 successes is 0.25, the probability of getting 1 success is 0.5,